Beginning with the excavation phase, heavy machinery deftly removes soil to create a precise pit matching the dimensions of the trampoline. Watching the ground gradually give way to reveal the earth below sets the stage for the exciting transformation ahead. As the excavation progresses, workers position the trampoline frame within the emerging pit. Guided by precise measurements, they lower the sturdy structure into place, ensuring it fits snugly and securely. This crucial step sets the stage for the subsequent assembly of the trampoline components. With utmost precision, the workers lower the trampoline frame into the excavated area, aligning it to ensure a perfect fit. Each corner is carefully checked to guarantee proper alignment and stability, essential for safe bouncing experiences. Their attention to detail not only ensures the trampoline rests securely within the pit, but also lays the foundation for countless hours of enjoyment and recreation, promising a haven for fun-filled moments in the backyard landscape. Next, the trampoline mat is carefully positioned, unfurling like a giant canvas over the frame. This process begins with leveling and smoothing the excavation area to create a stable base. Geotextile is then laid to provide additional reinforcement and prevent soil erosion. Concrete individual foundations are poured according to the specific dimensions of your pool, with Urban Pools XL requiring 8 metal struts and Urban Pools requiring 4. Before proceeding, the gravel layer is covered with polyethylene film to maintain integrity and prevent soil contamination. Reinforcement is then laid across the entire excavation area to enhance structural stability. The metal struts are assembled next, with 8 straight bars forming the upper part and 12 flat bars connecting the lower part. Finally, a concrete layer at least 3 centimeters thick is poured over a steel mesh, allowing for proper curing over a period of 3 weeks. Once the earthwork is complete, it's time to assemble the wooden structure of your pool. Begin by assembling the wooden construction, followed by the wooden planks. Start with the planks forming the wide face of the pool, ensuring tabs face upwards. Place the planks for the long edges of the pool on the corner pieces. Attach end profiles of the struts and assemble wooden wedges for the handrail, ensuring they are flush with the top of the wall. Mount the fittings to stabilize the handrail and keep it in position. To ensure effective filtration, carefully assemble the skimmer, taking care to tighten screws by hand to prevent damage. Next, install the inlet nozzle securely, ensuring proper alignment. Then, strategically place the filtration pipes to avoid any bends or kinks, maximizing the efficiency of water circulation and filtration within your massive wooden pool. During the assembly of automatic cover parts, it's essential to install the roller support bracket both outside and inside the wooden structure. This ensures proper support and functionality of the automatic cover system, allowing for smooth operation and effective pool coverage. To ensure a watertight seal and durable construction, attention to detail is crucial during the installation of the waterproofing membrane for your massive wooden pool. Begin by positioning each part of the clamping profile meticulously to ensure a seamless connection between components. It's imperative that the holes drilled for fasteners are precisely horizontal and perpendicular to the pool wall, guaranteeing structural integrity and a secure fit. Next, carefully apply the liner, ensuring it aligns perfectly with the pool's dimensions and contours. Pay close attention to the corners, ensuring they correspond precisely with the pool wall for a snug and seamless fit. Smooth out any wrinkles or creases in the liner to prevent potential leaks and maintain an aesthetically pleasing appearance. Before filling the pool with water, it's essential to install flanges at designated locations. These flanges provide additional reinforcement and sealing, ensuring the waterproofing membrane remains intact and effective over time. Installation of the flanges should occur once the water reaches specified levels, allowing for proper alignment and a secure attachment. Begin by sliding the shaft of the automatic cover flush with the wall passage, ensuring it fits snugly into place. Next, firmly press the shaft into the axle using a rubber mallet, ensuring it is securely seated. This step is critical for ensuring smooth operation and preventing any potential slippage or misalignment of the cover mechanism. After securing the shaft, attach the beams over the pool to support the automatic cover system. These beams provide structural reinforcement and ensure the cover operates smoothly and efficiently. Use O-rings at connection points to create a watertight seal, preventing water leakage and ensuring the integrity of the cover system. Additionally, install the partition wall and underwater light to enhance the functionality and aesthetics of your pool. The partition wall helps separate different areas of the pool, while the underwater light provides illumination for nighttime swimming and adds ambiance to your pool area. Extending the handrail 25 mm into the pool's interior ensures stability and safety. It also adds a finishing touch to the pool's design. Next, assemble and install the slat frames between the wall and the beam, ensuring they are positioned accurately. Secure tension bands to the slat frame to maintain tension and prevent sagging, ensuring the cover operates smoothly. Finally, mount the motor for the automatic cover by sliding the rubber ring onto the motor shaft. Ensure the rubber ring fits snugly to prevent slippage during operation. Insert the pin into the shaft recess securely, completing the installation of the motor. By following these detailed assembly instructions, you'll ensure the successful setup of your massive wooden pool, Urban Pools XL. With each step carefully executed, your pool will boast structural integrity, reliability, and longevity. From the initial earthwork preparation to the installation of the automatic cover and finishing touches, every aspect of the assembly process contributes to creating a luxurious and inviting backyard oasis. With your Urban Pools XL assembled according to these instructions, you'll enjoy years of relaxation and enjoyment with family and friends. Whether you're lounging poolside on sunny days or taking a refreshing dip to escape the heat, your massive wooden pool will be a focal point of outdoor entertainment and leisure. Upon stepping onto its platform, the magic unfolds. A spectacle of water emerges, rising gracefully to towering heights at the perimeter before delicately descending in a cascade, akin to the soft patter of a summer rain. The interplay of light and liquid creates an enchanting ambiance, inviting users to indulge their senses and bask in the moment. This garden shower is more than just a practical amenity, it's an oasis of rejuvenation. After an invigorating workout or a leisurely sunbathing session, its refreshing embrace becomes a welcome respite. The gentle caress of the falling water soothes tired muscles, while the revitalizing mist invigorates the senses, leaving one feeling invigorated and renewed. Baptist Hospital's sustainable design approach through prefabrication exemplifies a harmonious blend of efficiency and environmental responsibility. By embracing prefabricated materials, the hospital achieves accelerated construction timelines while meeting stringent sustainability targets. The utilization of prefabrication not only streamlines the building process, but also enhances quality control, fosters safer working conditions, minimizes waste, and promotes energy efficiency. From the innovative gate-light architectural facade system to the traditional prefabricated concrete panels, adorned with gate stone finish, every aspect of the design reflects a commitment to longevity and environmental stewardship. The project commenced with the construction of the first new filter bed, preceded by the careful demolition of the existing filter bed. The new beds were meticulously designed, each comprising 37 wall units standing at 2.50 meters in height, along with 208 filter bed tiles. Notably, the individual wall units were specially cored to accommodate feed pipes and washout pipes, emphasizing the attention to detail in the design phase. A key aspect of the installation was the unique stainless steel bolting system used to marry the filter bed wall panel units together. This innovative approach ensured structural integrity and stability, critical for the efficient functioning of the waste treatment process. Additionally, props were strategically employed to support every third concrete unit, while steel fixings were securely fastened, further enhancing the robustness of the system. Phase 1 of the project was successfully completed, marking a significant milestone with the first new bed brought into immediate operation. This was accompanied by the demolition of the old waste treatment plant, making way for the installation of the brand new filter bed system. The seamless transition ensured uninterrupted waste treatment operations, underscoring FP McCann's commitment to efficiency and reliability. A remarkable feat of engineering, the combined weight of approximately 50 tons of precast concrete filter bed wall and tiles, supplied from FP McCann's Littleport factory, highlights the scale of the undertaking. Despite the complexity and volume of materials involved, meticulous coordination ensured smooth progress throughout the project. During preparation, all loose and deteriorating concrete is removed to ensure a clean, porous surface for optimal bonding with TF structural deep repair mortar. Thorough removal is essential for a durable and long-lasting restoration of the staircase. Using 2x8s and duct tape, forms are constructed to match the desired shape and dimensions of the staircase. Care must be taken to protect the wood with duct tape to prevent unwanted bonding with the TF structural deep repair mortar. The forms are positioned and secured in place, ensuring they are level and properly aligned. Attention to detail is crucial during this phase to guarantee the final stairs meet structural and aesthetic requirements. Additionally, any necessary adjustments are made to accommodate variations in height and slope. Once the forms are in place, they serve as a mold for the TF structural application. The forms provide boundaries for the mortar, guiding its placement and ensuring uniformity across the staircase. Properly formed stairs result in a smoother application process and a more polished final outcome. During mixing, attention is paid to achieve the desired consistency. The mixture should be smooth and workable, allowing for easy application while ensuring it stays in place without flowing off the stairs. The proper consistency ensures optimal bonding and a uniform finish. Once the mixture is prepared, it is applied to the staircase surface using a trowel. Careful consideration is given to ensure even coverage and proper thickness, especially when applying a skim coat. The trowel is used to spread the overlay evenly, working it into the surface and smoothing out any imperfections. After the overlay is applied, additional tools may be used to refine the finish. For instance, a margin trowel can be used to round the edges of the steps, creating a smoother transition between the overlay and the existing structure. A broom may be used to create texture on the treads, enhancing traction and safety. Edge finishing involves using a margin trowel or similar tool to round the edges of the steps, ensuring a smooth transition between the overlay and existing structure. This process creates a polished appearance and minimizes the risk of chipping or unevenness along the edges of the staircase. Troweling and final swipes are critical steps in achieving a smooth and uniform finish on the concrete overlay. After the overlay mixture is applied to the staircase surface, a trowel is used to spread and work the material into place. This process helps to ensure even coverage and proper thickness throughout the stairs. During troweling, the goal is to eliminate any air pockets and inconsistencies in the overlay. The trowel is moved back and forth across the surface, smoothing out any imperfections and creating a seamless appearance. Care is taken to maintain a consistent thickness of the overlay, especially on the treads where traction is essential. Once the overlay is evenly spread and troweled, final swipes are made to refine the finish. This involves using the trowel to make smooth, sweeping motions across the surface, removing any excess material and creating a polished appearance. The final swipes help to blend any trowel marks or imperfections, resulting in a visually appealing finish. It involves thorough cleaning of the surface to remove any dust, debris, or other contaminants that could interfere with adhesion. Additionally, for surfaces made of clay, it's essential to moisten them appropriately. Level points or guides are then strategically placed to determine the desired thickness of the rendering, ensuring a smooth and even application process. During the placement phase of the sprayable rendering process, the prepared mortar mixture is loaded into the machine launcher. It's crucial to achieve the right consistency by gradually adding water until a creamy texture is attained, ensuring optimal workability. The nozzle of the mortar spraying device is positioned perpendicular to the surface, typically maintained at a distance of 10 to 15 centimeters. With precision, the mortar is projected between the level points or guides, covering the entire surface evenly. During leveling and finishing, the applied mortar is smoothed and leveled using appropriate tools such as wooden or rubber trowels. This process aims to create a uniform surface according to the desired finish. Once leveled, the mortar is left to reach the appropriate touch-dry stage before final finishing with a trowel. The project in Zederhaus, undertaken by Felbermayr, aims to address the escalating traffic volume on the A10 Tauern motorway, which reached 20,000 vehicles per day by 2017. Initiated in 2013, it involves enclosing a 1,500-meter section of the highway to mitigate the impact on local residents. The endeavor, endorsed by ASFINAG and governmental bodies, commenced with Felbermayr Tiefbau undertaking various tasks, including constructing bridges and widening the road. Significant efforts were made to accommodate the Zederhaus stream and maintain traffic flow during construction. This involved demolishing existing structures and employing shotcrete to stabilize slopes, covering an area equivalent to 4 football fields. Additionally, extensive use of anchors and concrete was necessary, with drilling depths reaching up to 15 meters. The enclosure process began with the construction of tunnel tubes, necessitating unforeseen shallow foundations to enhance ground stability. Fire safety concerns led to the use of concrete rather than asphalt within the tunnels. Construction proceeded with open methods, coupling formworks for efficient pouring of concrete sections. A total of 125 segments were required for the tunnel construction, utilizing fire-resistant fiber concrete with substantial wall thicknesses. Completion of the first tunnel tube in August 2015 marked a milestone, followed by the installation of electrical equipment and its opening to traffic in December 2015. The second tunnel tube's rough construction was completed in the same month, with subsequent sealing and membrane installation. Excavation for the enclosure began in February 2016, using material from the second tunnel tube's excavation. By March 2017, both tunnel tubes were operational, contributing to noise reduction for local residents. This was supplemented by the erection of noise barriers before and after the enclosure. In July 2017, ASFINAG granted final approval for the project's completion, acknowledging Felbermayr's successful execution despite adverse conditions. The Zederhaus project represents a significant achievement, demonstrating Felbermayr's capabilities in managing complex infrastructure projects. Despite challenges such as adverse weather and unforeseen ground conditions, the project was completed on schedule, providing relief to residents and enhancing safety for motorists. The steel used has a thickness of 1.2 millimeters, ensuring durability and structural integrity, while also providing sufficient strength to support the construction and withstand various environmental conditions. Steel shaping involves the process of manipulating steel materials into desired forms and configurations to meet specific structural requirements. This may include bending, cutting, welding, or forging the steel to achieve the desired shape and dimensions. Automated machinery may be employed to carry out these tasks with precision. Various techniques, rolling, pressing, or stamping, may be utilized, depending on the complexity of the design and the properties of the steel being used. Proper shaping is essential for ensuring structural integrity, aesthetic appeal, and functionality of the final product. Attention to detail during the shaping process is crucial to meet design specifications, optimize material usage, and ensure the longevity and performance of the steel components in various applications. Assembling the neck ring involves the careful construction and integration of a crucial component within a structure, typically found in applications such as tanks, vessels, or industrial equipment. The neck ring serves as a connection point or collar where other components are attached, or through which materials are transferred. The process begins with the selection of suitable materials for the neck ring, often steel or another durable metal alloy, chosen for its strength and corrosion resistance. These materials are then cut, shaped, and machined to precise specifications to ensure proper fit and functionality within the overall assembly. Next, the individual components of the neck ring are assembled according to engineering drawings or schematics. This may involve welding, bolting, or riveting the pieces together, depending on the design requirements and the materials being used. Skilled welders or technicians meticulously join the components, paying close attention to detail to ensure structural integrity and alignment. Once the individual components are assembled, the neck ring is integrated into the larger structure or system. This may involve welding or fastening the neck ring to other structural elements, such as tanks or vessels, using techniques that provide secure connections and maintain structural stability. Insulating with polyurethane foam involves applying a layer of foam insulation, typically 7 centimeters thick, to surfaces to improve thermal resistance and energy efficiency. Polyurethane foam is sprayed or poured onto the desired area, where it expands and hardens, forming a seamless barrier that prevents heat transfer. The insulation process begins with meticulous preparation to ensure efficient and safe application. Technicians must adhere to specific guidelines to drill 12mm injection holes through mortar joints, maintaining a consistent pattern across the cavity wall. Additional openings are made around areas like windows, doors, and eaves to guarantee comprehensive coverage. Each step of the process demands strict adherence to safety protocols. Technicians must don appropriate personal protective equipment, PPE, to mitigate potential health risks associated with handling insulation materials. This includes wearing gloves to protect the hands from chemical exposure and abrasions, overalls to prevent skin contact with the foam, boots to shield against slips, safety glasses to safeguard the eyes from debris, and a face mask equipped with appropriate filters to prevent inhalation of hazardous fumes. The face mask is particularly crucial as it helps prevent respiratory allergies and sensitivities by filtering out harmful particulates and organic vapors, such as the isocyanate component present in polyurethane foam. Before the actual injection of foam into the cavity walls begins, it's imperative to conduct rigorous quality checks to ensure the efficacy of the insulation. Samples of the foam are produced to assess various parameters, such as reactivity, adhesion strength, and cell structure. This preliminary step is crucial in identifying any potential issues before proceeding with the full-scale injection process. The foam is carefully dispensed into a polythene-lined container to prevent contamination and maintain its purity. Once dispensed, the reactivity of the foam is timed to ensure proper application. Technicians monitor the foam as it sets, paying close attention to its adhesion strength and the uniformity of its cell structure. Any deviations from the desired properties may indicate the need for adjustments or troubleshooting before proceeding further. To accurately determine the foam's density, it is dispensed into a container with a known volume and allowed to cure completely. After curing, the weight of the foam is measured and recorded. By dividing the weight by the volume, technicians can calculate the foam's density, providing valuable insights into its insulation effectiveness. With quality checks completed and parameters confirmed, the injection process commences. Foam injection proceeds methodically along each horizontal line of drilled holes, ensuring thorough coverage from the bottom of the cavity upwards. Dowels are utilized to mark filled injection points, preventing excess foam extrusion and ensuring precise application. Throughout the injection process, technicians must exercise caution to avoid over-injecting the foam beyond its cream time. Over-injection can lead to undesirable outcomes, such as splitting and shrinking, compromising the integrity of the insulation. Additionally, care must be taken to prevent overpressurization of the cavity, especially in closed areas like window frames, to avoid potential damage to the structure. Once each level of the cavity is filled, the set foam is carefully inspected to ensure proper adherence and uniformity. Technicians verify that the foam has adequately expanded and cured before proceeding to the next level. This approach guarantees that the insulation is applied effectively and delivers optimal performance in terms of thermal efficiency and structural integrity. Horizontal and vertical reinforcement hook bars streamline construction by simplifying installation processes. Their hook ends facilitate rapid alignment and connection, reducing labor time. These hooks interlock with other bars swiftly, ensuring a secure fit. Consequently, construction teams can expedite the placement of reinforcement, accelerating overall project progress. This efficiency not only saves time but also minimizes labor costs, making the construction process more economical without compromising structural integrity or safety standards. The process begins with careful planning and preparation, where builders evaluate the dimensions and specifications of the structural components involved. Each corner must be precisely measured and marked to ensure accurate placement of panels or elements during assembly. Next, corner brackets or connectors may be utilized to secure the structural elements together. These brackets are often made of durable materials such as steel or aluminum and are designed to provide robust support and reinforcement at the corners. They come in various shapes and sizes depending on the specific requirements of the project. During assembly, attention to detail is crucial to guarantee proper alignment and fitment of the structural elements. Builders must ensure that corners are square and true, using levels, squares, and other precision tools to verify alignment. Once the panels or structural elements are in position, fasteners such as screws, bolts, or welding may be employed to secure the corner assembly firmly in place. These fasteners are chosen based on factors such as load-bearing capacity, corrosion resistance, and structural requirements. Horizontal reinforcement installation involves placing steel bars parallel to the ground within concrete structures. This process enhances structural strength and durability by reinforcing the concrete against tension forces such as those experienced during earthquakes or high winds. Main panel installation involves positioning large structural elements, often prefabricated, in designated locations to form the primary framework of a construction project, such as a lift shaft or stairwell. Proper alignment and anchoring are crucial for structural integrity. Horizontal reinforcement and corner hook bars are steel components used in construction to strengthen concrete structures. Horizontal bars reinforce against tension forces, while corner hooks facilitate secure connections at corners, enhancing structural stability. Panels can be precisely cut to specified door length sizes, ensuring a tailored fit for door installations within a lift shaft or stairwell. This customization optimizes efficiency and accuracy in the construction process. Before laying tiles, prepare the substrate, ensuring it's clean, dry, and level. Verify flatness, adhering to the specified 1 mm deviation per 2 meters. Opt for a C2 class tile adhesive known for its enhanced adhesion, particularly ideal for flooring applications. This ensures the tiles adhere securely to the substrate, reducing the risk of displacement or cracking over time. Such preparation forms the foundation for a durable and aesthetically pleasing tile installation. Applying adhesive in a double layer is recommended to guarantee optimal adhesion and eliminate voids beneath the tiles. This method involves spreading a first layer of adhesive evenly across the substrate using a notched trowel. Subsequently, another layer is applied over the first, ensuring complete coverage and filling any gaps. The double layer technique ensures a strong bond between the tiles and substrate, minimizing the risk of air pockets and enhancing the overall stability and longevity of the tile installation. To ensure a flawless tile installation, it's crucial to eliminate excess air by tapping tiles gently from the center to the edges. This process prevents potential cracking or breaking during installation, guaranteeing tiles lay flat and securely. Using appropriate tools for joining tiles is essential, promoting precise alignment and minimizing irregularities. Employing a suitable leveling system is equally critical, maintaining a completely flat tile surface and preventing lippage between adjacent tiles. These practices ensure not only an aesthetically pleasing result, but also a durable and long-lasting tile installation, resistant to potential issues such as unevenness or displacement. T-type tile adhesive, specifically designed for wall tile applications, offers several advantages that contribute to a successful and secure installation. One of the primary benefits is its ability to reduce slippage during the installation process, particularly when working with larger or heavier wall tiles. The T-type adhesive, also known as thin-set mortar, is formulated with special additives that enhance its bonding properties and improve adhesion to vertical surfaces. This adhesive typically has a thicker consistency compared to standard tile adhesives, providing better support and minimizing the risk of tiles sliding down the wall before the adhesive sets. The unique formulation of T-type adhesive includes polymers and additives that increase its tackiness and reduce the likelihood of tiles shifting or slipping during installation. This is especially important when working with large format or heavy wall tiles, as their weight can put additional stress on the adhesive as it sets. Furthermore, T-type adhesive often has extended open times, allowing installers more flexibility to adjust tile placement before the adhesive sets. This is advantageous when working on intricate or detailed installations where precise alignment is critical. Another factor that contributes to reduced slippage is the texture of T-type adhesive. Many T-type adhesives have a gritty or rough texture that provides additional grip between the tile and the substrate, further minimizing the risk of slippage. Additionally, T-type adhesive is formulated to withstand vertical pressure and gravity, ensuring that tiles remain securely in place once installed. This helps prevent issues such as tiles sagging or shifting over time, which can compromise the integrity of the installation. Leveling the tile surface with a rubber trowel is a critical step in ensuring a smooth and uniform finish. After placing the tiles, use the rubber trowel to gently press them into the adhesive, ensuring they are properly bedded and any air pockets are eliminated. The rubber trowel helps distribute pressure evenly across the surface, promoting adhesion and preventing unevenness. Once the tiles are set and the adhesive has cured slightly, excess adhesive or grout must be removed to achieve a clean and polished look. This is typically done using a damp sponge, which is lightly run over the surface to wipe away any excess material. Care must be taken not to disturb the tiles while cleaning. This final step adds the finishing touch to the tile installation, leaving behind a professional and flawless result. The initial step in the trenchless shaft rehabilitation process involves the meticulous digitization of the shaft using cutting-edge 3D laser scanning technology. This advanced scanning equipment is strategically positioned within the existing shaft, ensuring comprehensive coverage of the entire structure. Controlled through an intuitive app interface, the scanner systematically captures detailed data points at 1-meter intervals from the top to the bottom of the shaft. The collected data is then processed using specialized software, where it undergoes intricate analysis and compilation. Engineers meticulously examine the digital representation of the shaft, leveraging the comprehensive 3D model to gain insights into its condition and structural integrity. This detailed model serves as a vital foundation for the subsequent stages of the rehabilitation process. Through the 3D model, engineers can identify any existing defects, deterioration, or anomalies within the shaft. From cracks and corrosion to deformations and misalignments, every aspect of the shaft's condition is meticulously evaluated. By conducting a thorough assessment, engineers can determine the most appropriate and effective rehabilitation measures to address any identified issues. Moreover, the digital model facilitates collaborative discussions among stakeholders, allowing for informed decision-making regarding the rehabilitation plan. Engineers can visualize the proposed interventions within the context of the digital model, enabling them to assess their feasibility and potential impact accurately. With the 3D model at their disposal, engineers can engage in collaborative discussions to devise an optimal rehabilitation plan. Factors such as structural integrity, material requirements, and project timelines are carefully considered during this phase. At the heart of the PREDL-FLEXLINER system lies precision engineering and meticulous craftsmanship. Using computer numerical control, CNC, milling technology, a negative mold of the new shaft collar is crafted. This mold serves as the template for producing the installation components required for rehabilitation. Skilled technicians meticulously manufacture the PREDL-FLEXLINER components, ensuring uncompromising quality and dimensional accuracy. Prior to the insertion of a section of the shaft, typically 66 centimeters, is excavated to accommodate the rehabilitation contribution. The is then carefully folded and inserted into the shaft non-destructively through the access point, known as the bonus. Specialized sealing bladders are strategically positioned to seal off inflows and outflows within the shaft. Additionally, styrofoam support bodies are introduced during backfilling to provide stabilization and prevent buoyancy once the is securely positioned within the shaft. Attention turns to the rehabilitation of the shaft rings. A smaller head, constructed from durable 3mm plastic material, is utilized for this purpose. Through meticulous welding techniques, the connection between the and the smaller head is established, ensuring structural integrity and longevity. Any protrusions or irregularities originating from the shaft rings are addressed and sealed with protective caps to prevent infiltration during backfilling. With the rehabilitation components securely in place, the final phase of the process commences. Grout mortar is meticulously introduced into the shaft to ensure proper backfilling and structural stability. The styrofoam support bodies, provided by PREDL, are removed, and the fully rehabilitated structure undergoes a thorough cleaning process. Finally, meticulous attention is given to the aesthetics of the rehabilitated shaft, with any imperfections addressed and rectified. Approximately 9,000 tunnel rings, each composed of 6 segments, are essential for constructing the dual Forrestfield Airport link tunnels. A custom concrete blend is formulated to meet stringent requirements for the tunnel segment construction. The concrete mix underwent rigorous examination, including extensive fire testing conducted in Germany and Victoria. These tests assessed its resilience and durability under high-temperature conditions, crucial for tunnel safety. Various other evaluations were performed, scrutinizing its strength, composition, and reaction to stress. The aim was to ensure the mix met international standards, guaranteeing optimal performance and safety within the tunnels of the Forrestfield Airport link, underscoring the applied in its development and validation. During construction, a steel reinforcement cage is meticulously installed within each segment. 2 distinct cage types are utilized, tailored to suit the specific location within the tunnel, ensuring structural integrity and alignment compliance throughout the Forrestfield Airport link construction process. Once the concrete is placed, skilled workers meticulously use trowels to smooth and perfect its exposed surface. This process ensures the desired finish, enhancing both the appearance and functionality of the tunnel segments within the Forrestfield Airport link, meeting stringent quality standards and ensuring optimal performance in service. The steam chamber, operating at 100% humidity and temperatures reaching up to 55 degrees Celsius, provides an ideal environment for the curing process. This controlled setting accelerates concrete strength development, promoting robustness and durability in the tunnel segments for the Forrestfield Airport link, ensuring their structural integrity. During curing, the segments are enveloped in insulated covers, maintaining controlled temperature and relative humidity for up to 72 hours. This prolonged period fosters an optimal curing environment, allowing the concrete to attain its desired strength and durability. This meticulous treatment ensures the tunnel segments for the Forrestfield Airport link achieve the necessary structural integrity and performance standards before deployment. Following segment construction, a meticulous application of 2 layers of waterproofing epoxy paint is undertaken on the external surface. This process serves as a protective shield, guarding against moisture ingress and environmental factors. The epoxy paint, renowned for its durability and sealing properties, forms a robust barrier, enhancing the longevity and resilience of the tunnel segments within the Forrestfield Airport link. This safeguarding measure not only bolsters the structural integrity, but also ensures sustained performance, minimizing potential degradation from water exposure and external elements, crucial for the tunnel's reliability and safety throughout their operational lifespan. Upon completion, each segment is delicately transferred to a tilting table, carefully maneuvered to facilitate further processing and quality checks. Once inspected and approved, these segments are moved to storage facilities, awaiting deployment by the tunneling team. The storage period allows for logistical coordination, ensuring the segments are readily available as needed during the construction phase of the Forrestfield Airport link. While in storage, measures are taken to preserve their integrity and quality, safeguarding against any potential damage or deterioration. This handling and storage protocol guarantee that the segments are in optimal condition and seamlessly integrated into the construction process, contributing to the efficient and precise assembly of the tunnels when required. Installing the supporting mesh involves affixing steel or synthetic mesh to tunnel walls to reinforce and prevent potential rockfall hazards. Shotcrete, a high-velocity sprayed concrete, is applied onto the tunnel walls post-mesh installation, fortifying the structure and enhancing stability against geological pressures and erosion. Drilling for securing anchors entails precision drilling into the tunnel walls or surrounding rock. Holes are strategically positioned to insert anchors, ensuring stability. Specialized machinery drills holes of specific depths and diameters, and workers carefully place anchors, often made of steel, securing them in place to fortify the structure against potential shifts or collapses. Securing anchors involves placing steel or concrete anchors into drilled holes, ensuring a secure fit. These anchors reinforce the tunnel walls, enhancing structural integrity and stability. Drilling the blasting holes is a process where specialized equipment drills holes of precise depths and orientations into predetermined locations within the rock face. These holes are strategically planned to facilitate controlled blasting. The drilling machinery carefully creates the necessary pattern and depth, ensuring the subsequent explosives are placed effectively for controlled fracturing and excavation during the blasting phase of tunnel construction. Preparing for the blast involves implementing safety protocols, evacuating personnel, and securing the area to ensure controlled detonation safety. Filling with two-component explosive involves precisely loading the drilled holes with measured amounts of distinct compounds, ensuring a controlled and effective blasting charge. Connecting the detonating fuses is a critical step in initiating a controlled explosion. After loading the holes with explosives, trained personnel meticulously connect the detonating fuses. These fuses serve as the link between the blasting caps or charges and the initiator, ensuring a sequential and controlled ignition. Workers carefully handle the fuses, ensuring they are securely attached to the explosives and properly insulated to prevent accidental ignition. Various safety measures, including proper grounding and insulation, are observed during this process to minimize risks. Each fuse's length is calculated to introduce a calculated delay between charges, enabling a sequential detonation pattern, crucial for controlled fracturing and excavation of the rock mass. Quality checks are conducted to verify the connection's integrity, ensuring they're free from any damage or defects that could compromise the detonation sequence. Any irregularities or faults are promptly addressed before the blasting operation. Clear communication among the team is essential during this phase to confirm that all connections are set correctly. Once confirmed, the area is further secured, and the initiation sequence is activated remotely, triggering the detonation process in a controlled and safe manner. Phase 1. Preparation and casting of surface A. The initial stage of this intricate process commences with the fastidious preparation of surface A. It begins with a meticulous cleaning routine, followed by the application of a release agent, ensuring a flawless separation once the panel is cured. Precision is key as mechanical extension arms are utilized to adjust the width of the panel, enabling seamless adaptation to desired dimensions. Subsequently, the bottom and top shutters are placed hydraulically, forming the fundamental framework for the panel. The critical attachment of window molds to surface A, facilitated by magnets, signals the commencement of the intricate assembly process. Simultaneously, the reinforcement is meticulously prepared and strategically placed atop surface A, meticulously prepared to withstand the concrete pour. With acute precision, concrete is poured, guided by calibrated markers or indicators meticulously placed along the shuttering. Vibrations then ripple through the newly poured concrete, ensuring optimal settling and cohesion. Following the concrete pour, the insulation layer takes its place, intricately affixed to the concrete through thermal pins that penetrate approximately 5 centimeters into the material. This layer not only fortifies the panel's insulation capabilities, but also aids in maintaining the concrete's temperature during the curing process. As surface A gradually attains a strength of around 9 megapascals through meticulous curing, preparations for surface B's creation take center stage. Phase 2. Transition to surface B and preparation upon surface A reaching the designated strength threshold. A carefully orchestrated sequence of hydraulic maneuvers tilts the horizontal table. This movement primes surface A for a pivotal transition as it is moved against surface B, necessitating the deactivation of the window shutter magnets. With precision, the two surfaces align, guided by closing pins and locking bars, securing their union. Surface B's preparation mirrors the precision and care exercised in Phase 1, encompassing a meticulous cleaning regimen, application of release agents, and the strategic placement of reinforcement and utilities. Phase 3. Panel extraction and conclusion. The culmination of this intricate process manifests in Phase 3, where meticulous attention to detail facilitates the seamless extraction of the completed panel. This phase involves a meticulous release of pins, shutters, and stoppers, allowing for the delicate detachment of the panel from the mold. The attachment of an overhead crane to surface B signifies the commencement of the extraction process. Through a carefully orchestrated sequence of mechanical movements, surface A elegantly transitions backward, ultimately lowering to a horizontal position. Subsequently, the loosening of surface B's side shutters culminates in the final separation, marking the completion of this intricate production cycle. At its core, Quikloc combines lightweight, easily accessible building materials with cutting-edge technology to craft precision-manufactured building panels. These panels undergo stringent quality control measures within a controlled factory environment, ensuring consistency and excellence. The result is a product that facilitates straightforward on-site assembly, overseen by semi-skilled workers requiring minimal trade skills. Preferred builders like Ultra Build exemplify the efficiency of the Quikloc system, erecting stylish and high-quality homes in a fraction of the time typically needed. The technology behind these structures allows for small exteriors that belie spacious interiors, maximizing living space. The system's efficiency is evident in its components: laser-leveled in-situ formwork for rapid floor surface preparation, standardized 1,200 mm panels color-coded for simplicity during on-site assembly, and aluminum extrusions minimizing site waste and cleanup. Installation follows a straightforward process utilizing heel and toe connections, with top and bottom plates, ensuring strength and stability. Aluminum blades lock panels securely in place, forming waterproof and architecturally pleasing joints. Windows integrate seamlessly, with sub-panels accommodating height variations, and preformed holes within panels facilitating the installation of electrical and plumbing services. For roofing, the Quikloc system combines traditional roofing methods with standard trusses and lightweight roof sheathing. This innovation extends beyond mere construction. It incorporates thermal and sound efficiencies across diverse accommodation styles, accommodating internal fixings and finishings with ease. It commences with the actual production phase, where a high-strength concrete mix. Following production, daily module extraction takes place, ensuring timely demolding once the concrete has properly set and cured. These extracted modules are then transported to the construction site for installation. The construction team swiftly proceeds with slab construction, laying the groundwork or foundational slabs where these precast modules will be integrated. Upon module delivery, the streamlined installation process takes center stage. Remarkably, within a mere 3 hours, 6 precast modules are seamlessly installed, showcasing the efficiency and speed inherent in this construction technique. By day 10, the project is already underway, emphasizing the swift progress achievable with precast concrete. As the construction progresses, a significant focus emerges on module installation within the internal areas, such as internal hallways. These precast modules, designed for precision and functionality, are strategically placed, optimizing space and structural integrity. The utilization of precast concrete not only accelerates construction, but also ensures consistent quality and strength, providing a robust framework for the building's internal spaces. In essence, the use of precast concrete modules revolutionizes the construction industry by significantly reducing project timelines, optimizing efficiency, and maintaining exceptional structural strength. This method not only enables swift completion, but also ensures reliability and durability in the long term.
At Lightcrete, they excel in creating lightweight precast concrete elements, especially tailored for residential projects. Their drafting department converts architectural specifications into production drawings. The workforce is highly skilled, boasting extensive experience, ensuring quality throughout the manufacturing process. One unique aspect is their use of pumice instead of crushed rock aggregate, resulting in a 50% weight reduction and enhanced benefits. They employ Golden Bay cement, a mix with a historical lineage dating back 2,000 years, even used in ancient constructions like the Pantheon. Their recent project in Flatbush showcases their capabilities. A 67-lot development, comprising 6 different house designs, saw the panels painted and installed before shipment to the site. The installation process involves lifting and lowering panels onto previously cast starters embedded in the floor slabs, showcasing a straightforward yet efficient method. These precast panels offer outstanding insulation and acoustic properties, meeting building codes without the need for interior stripping and lining. They emphasize the durability of their product, asserting resistance to rot and leaky home syndrome, providing energy-efficient homes with extended fire resistance ratings.
The project began with an ambitious goal: to erect a 15-story hotel in record time. What sets this construction apart is the breakneck speed at which it was accomplished. Over the course of just 6 days, a team of dedicated workers, operating around the clock, transformed an empty plot of land into a towering hotel. This is a testament to the incredible efficiency and skill of Chinese construction crews. The hotel's construction followed a meticulously planned process. It started with laying the foundation, which was a remarkable feat in itself. Each floor was then assembled with precision, and the building steadily rose into the sky. The use of advanced construction techniques and materials allowed for such rapid progress, ensuring the safety and stability of the structure. Perhaps the most astonishing aspect of this project is its ability to withstand a 9.0 earthquake. This demonstrates China's commitment to engineering excellence and safety standards. The builders spared no effort in ensuring the hotel's structural integrity. This incredible construction achievement is a testament to China's capacity for innovation and efficient project management. It's a reminder that in the modern world, where speed and quality are paramount, remarkable feats like this hotel's construction are possible. It stands as a symbol of China's commitment to pushing the boundaries of what is achievable in the world of construction. Precast construction is a modern and innovative method of building houses that offers a multitude of advantages, including speed of construction, high-quality materials, and superior cost control. Precast construction begins with the fabrication of molds for individual concrete units, each designed according to the specific requirements of the project. These molds are then filled with a specially mixed GGBS cement blend, which is prepared on-site. This approach breaks down the construction of a house into a series of individual concrete pieces. One significant advantage of precast construction is that it allows for meticulous attention to the look and finish of each concrete unit. Advanced techniques can be employed to achieve a higher quality product with greater precision. Before the concrete units ever reach the construction site, each piece undergoes thorough quality control checks to ensure consistent high quality. One of the distinguishing features of precast construction is that the concrete units are designed on-site and manufactured in a specialized factory, known as a stress light factory. Once the units are ready, they are transported to the building site and placed into position rapidly and accurately. This process significantly accelerates the construction timeline. A typical precast frame package includes various components such as columns, beams, floors, wall panels, stairs, landings, and balconies. With a substantial portion of the house being constructed using precast elements, the overall build time is significantly reduced. In some cases, it is possible to witness the construction of a 3-story house up to roof level in as little as 4 on-site days, showcasing the remarkable speed of precast construction. Precast construction also offers a wide slab precast composite floor system that can accommodate spans of up to 10 meters. This system is highly adaptable and quick to install on-site, reducing the need for numerous columns or joints. It allows for immediate safe access for all trades on-site. Precast stairs, manufactured in the Stress Light factory, are also inserted into the house swiftly and easily. This not only expedites the construction process, but also enhances on-site safety and creates a better working environment for all involved. Safety is a paramount concern in construction, and precast construction excels in this aspect. Precast floors, walls, and stairs provide superior fire resistance, durability, and strength compared to traditional concrete block construction. This not only ensures the safety of the occupants, but also enhances the long-term value of the house. Another advantage of precast construction is its exceptional acoustic insulation properties. Test figures reveal that a 150 mm concrete floor can achieve airborne sound insulation as high as 50 decibels. This ensures a quieter and more comfortable living environment for the residents. The speed and simplicity of the precast construction process also offer flexibility in layout and design. Internal walls can be modified, and load-bearing walls can be replaced by beams, accommodating changes in the design without significant delays or complications. Furthermore, the quick construction method allows various trades to plan and execute their services efficiently. This minimizes the likelihood of wandering pipes and conduits, contributing to better maintenance and management of the home in the future. Precast construction is not only advantageous from a construction perspective, but also from an environmental standpoint. The materials used to create precast slabs are sourced close to the Stress Light factory, reducing transportation distances and the use of fossil fuels. Additionally, this construction method reduces the overall amount of concrete used in a house by up to 20%, and the generation of construction waste on-site is nearly eliminated. This makes precast construction an environmentally friendly choice. When beginning to stack ICF blocks, it's essential to take advantage of the even interval height steps provided. This allows for a systematic approach to stacking. Each block fits neatly on top of the other, ensuring a stable foundation. Lock each block in place securely before moving on to the next one, in cases where unique architectural features are needed, like the circular tower in the hilltop house mentioned. Specialized radius blocks, like bill block radius blocks, can be used. These blocks are designed to create curved structures smoothly and efficiently. While stacking ICF blocks, it's essential to incorporate horizontal rebar reinforcement as specified by engineering plans. This reinforcement helps to strengthen the walls and provide structural stability. Once all the ICF blocks for the basement walls are stacked, it's time to brace and install scaffolding. The purpose of this is to prepare for the concrete pour. Properly bracing the walls ensures they can withstand the weight of the concrete. Using the installed scaffolding, vertical rebar reinforcement is added. This reinforcement runs between the two courses of ICF blocks and further enhances the structural integrity of the walls. At times you may need to cut ICF blocks to fit specific dimensions. To do this, a table saw can be used to make horizontal cuts. It's crucial to ensure that the cut is precise, aligning with your construction plans. For any parts the table saw cannot reach, a sawzall can be employed to complete the cut. Be mindful to cut the web on the same side as your notch to minimize waste. After making cuts, it's essential to clean up any rough edges or remaining web sections. This can be done using nippers or other appropriate tools to ensure a smooth and secure fit between blocks. Depending on your construction requirements, you may need to adjust the height of the ICF wall courses. In some cases, you may trim a course to fit precisely with your design plans. This is often necessary when working with architectural elements like the build deck mentioned in the document. In the example provided, the basement height is specified as 9 feet 4 inches, with an 8-inch build deck to be poured on top. The number of courses is adjusted accordingly to achieve the desired height, ensuring a seamless transition to the subsequent construction phases. The slip-form construction method has revolutionized the way large concrete structures like silos are built, offering efficiency, precision, and speed in the construction process. A notable example of this technology's successful application is the construction of a 25-meter high run-of-mine (ROM) concrete silo for Asmang BREP in the Northern Cape, South Africa. Designed by the engineering firm DRA and constructed by Stefana T. Stocks Civils, this impressive structure showcases the capabilities of slip-form construction. The Asmang BREP silo serves a crucial purpose in the mining industry, providing a secure and efficient storage solution for bulk materials. Its cylindrical shape and towering height of 25 meters make it a prominent feature in the landscape. But what sets it apart is the slip-form construction technique used in its creation. Slip-form construction involves continuously pouring concrete into a moving formwork that gradually rises, creating a seamless and structurally sound concrete structure. In the case of the Asmang BREP silo, the slip-form method was used to construct 4 equal quadrants, ensuring uniformity and strength throughout the structure. One of the key advantages of slip-form construction is its ability to achieve high precision and consistency. The concrete is poured at a controlled rate, resulting in a smooth finish and uniform thickness. This precision is vital in ensuring the silo's structural integrity and longevity, especially in the challenging conditions of the mining industry.
At the heart of their innovation lies the utilization of locally available materials, such as desert and river sand, ash, and other indigenous resources. These materials are ingeniously bound together to form robust building blocks, serving as a sustainable alternative to traditional cement and clay bricks. One of the remarkable features of Polycare's moss is its simplicity and efficiency, enabling the construction of a house within a remarkably short time frame of 2 to 3 weeks. The pre-designed nature of the buildings minimizes waste, ensuring optimal resource utilization throughout the construction process. Moreover, the modular design facilitates future expansions or additions, accommodating evolving requirements with ease. The polymer concrete building blocks developed by Polycare exhibit exceptional properties that surpass those of conventional construction materials. These blocks boast superior hardness compared to concrete while maintaining lower weight and exceptional size and shape tolerances. Notably, they are impervious to water absorption, rendering them completely windproof, frostproof, and corrosion-resistant. Their high resistance to UV radiation and temperature variations further enhances their durability and longevity. Beyond structural integrity, Polycare's building blocks incorporate built-in insulation, contributing to energy efficiency and thermal comfort. This inherent insulation reduces the need for additional heating or cooling systems, keeping buildings naturally cool in summer and warm in winter. Begin by marking the outline of the wall and driving stakes into the ground at 3-foot intervals. Secure the spider ties to the stakes, ensuring they are positioned correctly for the desired wall shape. These ties will hold the concrete in place during pouring and curing. Preparing the footing is a critical step in ensuring the stability and longevity of the monolithic concrete wall. To accomplish this, the process begins with the utilization of pre-mixed dry sack cement. Upon obtaining the dry sack cement, the next step involves wetting it down with water. This hydration process activates the cement, causing it to bind together and form a cohesive mixture suitable for creating a stable foundation. Much like setting fence posts, this wetting down process ensures that the dry cement mixes thoroughly with the water, creating a consistent and workable material. Once the dry sack cement is adequately moistened, it is applied to the designated area where the wall's footing will be established. Determining the desired height of the wall is a crucial aspect of the construction process, as it dictates the overall appearance and functionality of the structure. Before proceeding with the wall building process, careful consideration must be given to ensure that the height aligns with both aesthetic preferences and practical requirements. To begin, the contractor or designer evaluates the landscape's contours and the intended purpose of the wall. This assessment helps determine whether the wall should follow the natural slope of the terrain or maintain a consistent level. For aesthetic purposes, the height may be adjusted to create visual interest or complement surrounding features. Once the desired height is established, it is marked along the length of the wall using measuring tools and chalk lines. Achieve the proper mix design for the concrete to ensure optimal flow and strength. Begin building the wall using the spider tie system, stacking the ties up to 4 feet high and adding rebar for reinforcement as needed. Customize the wall as desired, adding features such as cantilever edges or decorative elements. At the heart of the A-fold concept lies its modular design, which allows for easy assembly and disassembly of prefabricated components. Constructed primarily from wood, a renewable and environmentally friendly material, the A-fold house offers a harmonious blend of modern aesthetics and sustainable living. The construction details of the A-fold house reveal meticulous planning and innovative engineering. Each module is precision engineered off-site, ensuring consistent quality and minimizing on-site construction time. This not only reduces environmental impact, but also streamlines the building process, enabling quicker occupancy. Maslow Homes, the Spanish partner in this venture, brings local expertise and insight, ensuring that the A-fold house aligns seamlessly with Spanish architectural and environmental standards. By partnering with a local firm, A-fold demonstrates its commitment to adapting its modular housing solution to diverse geographical and cultural contexts. Furthermore, the A-fold house in Spain exemplifies adaptability. Its modular design allows for easy customization and expansion, catering to the evolving needs of homeowners. Whether used as a primary residence, vacation home, or temporary shelter, the A-fold house offers versatility without compromising on sustainability or durability. One of the key features of the StormTrap system is its versatility. It can be customized to accommodate various site requirements, including size constraints and specific load-bearing needs. Additionally, the modular design allows for easy installation and scalability, making it suitable for both small-scale residential projects and large commercial developments. The StormTrap system employs a combination of infiltration, detention, and retention techniques to manage stormwater effectively. During periods of heavy rainfall, excess water is captured and temporarily stored within the system. gradually releasing it back into the environment or allowing it to infiltrate into the ground. This helps to alleviate pressure on municipal stormwater infrastructure and reduce the risk of downstream flooding. Furthermore, the storm trap system promotes sustainable water management practices by facilitating rainwater harvesting and groundwater recharge. By capturing and storing stormwater for later use, it helps to conserve water resources and mitigate the impact of drought conditions. One of the standout features of the EPG 400P is its compact and lightweight design, which allows for easy transportation to job sites. This portability is further enhanced by its cordless operation, eliminating the need for a connection cable to a transformer. As a result, setup time is reduced and maneuverability is improved, particularly in tight spaces or areas without easy access to power sources. Despite its small size, the EPG 400P packs a punch in terms of power and performance. With a 500-watt motor, it delivers efficient sanding and polishing capabilities across various surfaces. The sander's low rotational speed, ranging from 0 to 100 revolutions per minute with electronics and 85 revolutions per minute under load, ensures precise control, comparable to manual sanding techniques. This feature is especially beneficial for delicate tasks such as ceiling finishing, corner trimming, and vertical wall cleaning, where precision is paramount. When it comes to smoothing rough mortar, a hard disk attachment for power tools like angle grinders or finishing sanders can be invaluable. These hard disks are typically equipped with abrasive materials, diamond or carbide grits, allowing them to effectively grind down rough surfaces and uneven patches of mortar. They provide a quick and efficient solution for achieving a smooth and uniform finish, making them essential tools for masonry and construction professionals tasked with mortar preparation and surface refinement. A backing pad with metal plates and tobacco sponge serves as a versatile tool in various industries, particularly for polishing and finishing applications. The metal plates provide stability and durability to the backing pad, ensuring consistent performance under pressure. Meanwhile, the tobacco sponge, known for its absorbent and resilient properties, offers cushioning and flexibility, allowing for smooth and even surface contact during polishing tasks. This combination enhances efficiency and precision in surface refinement processes. Before starting the edging process, professionals clean the edges of the asphalt surface. This involves removing any debris, dirt, or vegetation that may obstruct the application of the seal coat. Additionally, they inspect the edges for cracks or damage that might require repair before sealing. To prevent seal coat overspray onto adjacent surfaces, such as concrete, grass, or buildings, the pros use masking tape or specialized edging tools. This precise masking ensures a clean boundary and minimizes cleanup efforts later. The key to achieving flawless edging lies in the technique. Pros typically start by applying a thin line of seal coat along the edge, using a brush or edging tool, ensuring even coverage. They then feather out the seal coat slightly onto the adjacent surface to blend seamlessly. Attention to detail. Professionals pay close attention to detail throughout the edging process. They take their time to ensure every inch of the edge is properly coated, avoiding missed spots or uneven application. Quality sealant. Using high-quality sealant is paramount in achieving long-lasting results. Professional seal coaters select premium sealants formulated with durable additives that provide superior protection against UV rays, water damage, and other environmental factors. Styrofoam thermal bricks have emerged as a revolutionary solution in the construction sector, particularly catering to the varying degree day regions in Turkey. Developed to meet the stringent UD values required for constructions in the 3rd and 4th regions, these bricks offer unparalleled thermal insulation without the need for additional manufacturing processes. The second and third model styrofoam thermal bricks have been designed to adhere to the Lambda 23.8 values, certified by the prestigious UTO certificate issued by ITBAK. This certification ensures not only compliance, but also guarantees quality and performance. Available in two dimensions, 190 by 190 by 135 mm and 240 by 240 by 135 mm, with varying wall thicknesses, these thermal bricks are versatile and adaptable to different construction needs. What sets them apart is the incorporation of carbon-reinforced styrofoams, produced with a density of 16 to 18 kilograms per cubic meter, which enhances their structural integrity and insulation properties. The synergy between the thermal bricks and carbon-reinforced styrofoams is seamless, thanks to engineering and manufacturing processes. Furthermore, the special packaging ensures that these components reach the construction site intact and ready for application. One of the standout features of these thermal bricks is their user-friendly design. Equipped with special half-cut edges for corner application and a staggered pattern for optimal installation, they facilitate easy and efficient construction practices. Whether it's a new build or a renovation project, these bricks can be seamlessly integrated into any construction endeavor. The construction involves Bertha, the tunnel boring machine, not only excavating dirt but also actively contributing to the tunnel's creation by installing concrete rings. These rings, comprising 2-foot-thick concrete segments, form the tunnel's circumference. Resembling a jigsaw puzzle where precision is paramount, the initial focus lies on building the foundational elements for the roadway. This begins with constructing the corbels, the crucial base for placing walls and decks. The concrete used in this phase is reinforced with rebar, ensuring durability against concrete expansion and contraction. After setting up formwork, concrete is poured into the corbel framework. Once poured, the concrete is covered and left to cure for about 28 days, gradually gaining strength over time. Simultaneously, crews work on erecting the tunnel walls, comprised of reinforced concrete panels weighing 13 tons each. The meticulous process involves setting the reinforcing steel, placing forms, and pouring concrete to create sturdy, upright, sandwich-like structures. Once the walls are completed and cured, attention shifts to the upper roadway deck. This involves intricate processes, including ensuring access beneath the deck for the tunnel boring machine and applying special coatings to prevent corrosion on reinforcing steel. Pouring concrete for the upper roadway deck is a collaborative effort, with various team members handling specific tasks to ensure top-notch quality and finishing. The goal is to create a smooth and durable roadway surface, crucial for drivers' safety and comfort. As the upper deck nears completion, efforts turn to the lower roadway, which sits atop the corbels. This section is precast off-site for efficiency and set in place toward the project's conclusion. The magnitude of this construction project is evident in the sheer volume of concrete used, enough to build 9 football stadiums. Once finished, the State Route 99 tunnel will stand as one of the longest roadway tunnels in the United States, promising to transform Seattle's waterfront and revolutionize transportation in the region. Between April 17, 2018 and July 27, 2018, the SS1 Nuova Aurelia witnessed an extraordinary engineering feat carried out by the tunnel boring machine, TBM, named Lucia. Nestled within the expansive construction site, the TBM Lucia became a formidable force, delving deep into the Earth's crust to carve out 3 significant tunnels, Baschi, S. Paolo, and Cappuccini. These tunnels, collectively spanning an impressive 3,500 meters, stand as a testament to human ingenuity and determination. The inception of this monumental endeavor marked a new chapter in modern construction, as the TBM Lucia, resembling a colossal metal serpent, commenced its relentless journey beneath the surface. With unwavering precision, this mammoth machine bore through layers of rock and soil, shaping pathways that would soon become vital conduits for transportation and connectivity. The first of these tunnels, Bashi, unveiled itself as a triumph of engineering prowess. Stretching through the subterranean expanse, it ran for a considerable distance, weaving its way through the natural geological formations with unparalleled accuracy. As Lucia diligently progressed, S. Paulo emerged as the next testament to its unwavering determination. This tunnel, a testament to human perseverance, added to the tally of impressive accomplishments, further solidifying the TBM's significance in this ambitious project. Undeterred by the challenges inherent in tunneling, Lucia navigated its way through the earth with an almost relentless fervor, carving the Cappuccini Tunnel into existence. Each meter carved was a testament to the collaboration between human intellect and technological marvel. These tunnels not only represented physical passages, but also stood as metaphors for the triumph of human endeavor over seemingly insurmountable obstacles. As the TBM Lucia completed its monumental task of excavating these tunnels, a different phase of the project ensued. With the tunnels now carved out, meticulously crafted, and ready to serve their intended purpose, attention turned to the process of dismantling the colossal machine. The dismantling process was a symphony of engineering expertise and precision. Each component of the TBM, designed and assembled for the singular purpose of tunnel excavation, was disassembled with careful consideration. Teams of skilled technicians and engineers meticulously ensured that every piece was carefully removed, catalogued, and prepared for future use or recycling. The process, while methodical, also held a touch of nostalgia. Lucia, the indomitable machine that had burrowed tirelessly through the earth, had become more than a mere piece of equipment. It had become a symbol of human ambition and the unyielding pursuit of progress. As the final pieces of Lucia were disassembled and removed from the site, they left behind not just a series of tunnels, but a legacy of innovation and perseverance. The 3,500 meters of excavated tunnels stood as a testament to human capabilities and the relentless pursuit of pushing boundaries in the realm of construction and engineering.